Yeah, good afternoon, students. Good afternoon once again. So, am I visible and audible to all of you? Yeah, good afternoon, Virendra. Good afternoon. Is my screen visible to all? Okay. From JNV Bell. Yes. Okay. So, we are in chemical bonding, right? So, today we are about to start the hybridization part. So, yesterday, what we have discussed, the VSEPR theory and the valence bond theory we have discussed. So, today let's start with the hybridization. So, what is hybridization? And before that, who proposed this hybridization means Linus Carl Pauling. So, this Pauling scientist only proposed this hybridization concept. Okay. So, he took atomic orbitals with slightly different energy. Okay. And when he combined these two, he got hybrid orbitals with equivalent energy. Now, he said that only these hybrid orbitals are used in the bond formation process. Okay. Now, coming to the definition of hybridization, it is the intermixing of atomic orbitals of slightly different energy so as to redistribute their energies, resulting in the formation of new set of orbitals of equivalent energy and shape. Okay. So atomic orbitals are intermixing with each other to give the hybrid orbital, and these hybrid orbitals are forming the electrons which are present in hybrid orbitals are forming the bond with the other atom. Okay. So this is the definition for hybridization. It is the intermixing of atomic orbitals. So this is very important. Okay. Now coming to the features of hybridization, some of the salient features of hybridization. Feature number one is the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. Suppose if I am taking 2s and 2p. So how many atomic orbitals I am mixing? 1 2s and 3 2p orbitals are mixing with each other. So totally I am going to mix 4 orbital. Okay. So I will get 4 hybridized orbital. If 4 atomic orbitals are intermixing with each other, 4 new hybrid orbital will be formed. Okay. Now 1s and 3p. So sp3 hybridized orbital is forming and 4 sp3 hybridized orbitals are forming. Got it? The number of the number of hybrid orbital is equal to the number of atomic orbitals that is being combined or that is getting hybridized. Okay. Coming to the second point, the hybridized orbitals. So this sp3, this 4 sp3 hybridized orbitals, they are always equal in energy and equal in shape. Okay. So equal energy and shape will be there for the hybridized orbital. Coming to the third point, coming to the third feature, the hybrid orbitals are more effective in forming the bond than the atomic orbital. So if mostly the shape of the hybridized orbital will be like this. One lobe will be bigger than the other. But in case of normal atomic p orbital, if I take, I will have the shape like this. Okay. Now, if two normal atomic orbitals are forming the bond with each other means the overlapping area will be like this, no? For normal atomic orbital. But for hybridized orbital, if I take, this is the shape of one hybridized orbital and this is the shape of the second hybridized orbital. And here you see the overlapping area will be more in case of hybridized orbital because one lobe is bigger than the other, right? Since the overlapping area is more, the strength of the bond will be more. So hybrid orbitals are more effective in forming the stable bonds than the pure atomic orbital. Got it? Now coming to the fourth point, hybrid orbitals are directed in space in some preferred direction to have minimum repulsion between the electron pairs and the stable arrangement. So yesterday we have discussed VSEPR theory, right? So in that, in one point we have seen that lone pair will try to occupy the maximum distance between them. So because of the repulsion. So the same case is followed here also. So you see here, the hybrid orbital will try to occupy the space or it tries to prefer the direction to have the minimum repulsion. In case of CH4, we have a carbon and 4 hydrogens attached to it. The hybridization of this carbon is sp3. So if it is sp3, we have 4 sp3 hybridized orbital formed. So this is the first sp3, this is the second sp3, and this is the third sp3, and this is the fourth sp3. So all the 4 sp3 hybridized orbitals are occupying the space in which they have minimum repulsion. Got it? And they are overlapping with the oneness atomic orbital of hydrogen and forming the sigma bond. Got it? So any doubt from the hybridization definition and the features of hybridization for JNV Ramnagar and for Virendra? Yes or no? No. Okay, everything is fine. So now let's see the types of, okay, good. Let's see the types of hybridization. So we have 2 different combination of mixing, okay, of this atomic orbital. One is s orbital and p orbital mixing, and the other one is spd. All the 3 orbitals, when if they mix with each other, they will also produce some type of hybridization. First, let us see one by one. Yeah, for S and P, we have 3 combination: SP, SP2, SP3, and for this SPD, again 3 combination: SP3D, SP3D2, SP3D3. So these are the types of hybridization. Okay. Now, how to find out the hybridization of the central element just by looking at the formula? So how to do that? So if I have to find out this hybridization, I have to first take out the atomic number of that central element. Then I have to find out the valence electrons of that element. Then using that valence electron, I have to intermix the atomic orbitals in which only one electron is present. So we have, it is a tedious process. Okay, and we have to draw the shape. Then only we can find out. But in this session, I am going to give you a trick to find out the hybridization. Okay, a trick to find out the hybridization. So you have to use just only one formula, and that formula is electron pair equal to bond pair plus lone pair. Electron pair is equal to bond pair plus lone pair. So before explaining this, I'll tell you how we have to find out the hybridization using the complete theory. Okay, so that also you see, I'll teach that for only one system. I'll teach for sp hybridized system. Okay, so rest all is not required. For the other things we can use the trick itself, but still for your information I just want to give I just want to take one type and explain you. Okay, so let us take this sp. So in this sp, what example I can take? Yeah, beryllium chloride. Okay, beryllium chloride is taken as an example. Now, who is the central atom? Beryllium or chlorine? Who is the central atom? Beryllium or chlorine? Yes, good. Beryllium is the central atom. What is atomic number of beryllium? Very good. It is 4. Electronic configuration of beryllium is 1s2 and 2s2. Very good. Very good, students. Yes, it is. So 1s2 and 2s2. Now the valence shell is the second shell, and in that shell we have 2 electrons. So this is the 2s orbital in which it has 2 electrons. Now, since beryllium belongs to the second period, it also has 2p orbital. It also has 2p orbital, but it will be empty. Okay, so this is the ground state electronic configuration for beryllium. Now coming to the excited state, if I give some energy, one of the paired electron will jump to the empty orbital. So in this case, I will have 1 electron in 2s and 1 electron in 2p. Okay. Now these 2 orbitals which has 1 electron each, that will intermix with each other. Okay. So if 1s and if 1p mix with each other, what I will get? I will get sp hybridized orbital. Now, since 2 atomic orbitals are mixing with each other, we will get 2 hybridized orbital. So this is the first sp orbital and this is the second sp hybridized orbital. Okay, so it will be there for beryllium. So beryllium is at the center. So this is the first sp and this is the second sp, in which 1 electron is located. And with this chlorine orbital, chlorine p atomic orbital, p orbital of chlorine, it will come and form the bond with beryllium. Okay. So this is the normal atomic orbital of chlorine, but this is the hybridized orbital of beryllium. Now they are forming BeCl bond like this, and they are 180-degree angle with each other. And now the shape of the beryllium chloride is linear. Okay. So this is how we have to find out the hybridization shape and the bond angle for a given formula. Okay, given compound. So without doing all these things, okay, we are taking this formula and getting the hybridization easily. Okay, electron pair is equal to bond pair plus lone pair, or we can call this as steric number also. Steric number is equal to number of sigma bond plus number of lone pair. You can use this formula also. Both are same. Both are same. Hybridization of which atom? Hybridization of which atom in CN? Hybridization of which atom, Virendra? CN is C triple bond N, right? So carbon is having 3 bond. Means it is sp hybridized. It is sp hybridized. So here one is sigma and the other two are pi. If a system has 2 pi bond, then it is sp hybridized. Okay, I'll explain you. Now use this formula. Okay, so we can take this beryllium chloride also. BeCl and Cl, no. So this is the thing. Take the central atom, find out the steric number or the electron pair. So what it is? Bond pair or number of sigma bond? Both are same only. So how many sigma bonds does this beryllium has with it? Here one and here one. So totally 2 sigma bond, and there is no lone pair, because all the 2 valence electrons of beryllium has been used for bonding, right? So the 0 lone pair, steric number is 2, or the electron pair number is 2. Okay, if it is true, then the hybridization is sp. So that is what we have found out there, right? So the hybridization is sp. Okay, got it? Now one more example, if I want to take, you can take H2O itself. H2O. So HO and H. So oxygen has 2 lone pair and 2 bond pair, right? So the number of sigma bond or number of bond pair itself you can keep. Bond pair, 2 bond pair and 2 lone pair. So the electron pair is 4. If the steric number or electron pair is equal to 4, then what is the hybridization? It is sp3. So the hybridization of this oxygen is sp3. Okay, you can take NH3. Nitrogen has 5 valence electron, 3 for bond pair and 2 is present as 1 lone pair. So totally 3 bond pair and 1 lone pair. Answer is coming out to be 4. So the hybridization is sp3. Okay. Now in case of C2H2, C triple bond C, H and H. Okay. Now how many bond pair here? How many sigma bond? We have to find out the sigma bond. So 1 and 2. So others are pi bond. So here only 2 sigma bond and there is no lone pair. So the total number is 2. So it is sp hybridized. Got it? So this is how we have to find out the hybridization. If the answer is coming out to be 3, then it is sp2. For sp2, what example? BF3 we can take. So this is BF3. It has 3 bond pair and no lone pair. So 3 plus 0 will be 4. 3 plus 0 is 3. Okay, 3 plus 0 is 3. Okay, so you want me to explain C2H2 once again? Okay, I'll explain. Let me just complete this BF3 part and then come to that. Okay, so it is 3. So if it is 3, then the hybridization is sp2. Now C2H2, coming to C2H2 has 2 sigma bond and 2 pi bond. You have to take only the number of sigma bond. That is a bond pair. Okay. Now there are 2 sigma, so 2, there is no lone pair, so 0, 2 plus 0 is equal to 2. If the electron pair is equal to 2, then it is sp. Okay. For sp3D, we can take PCl5 as an example. in which you will have 5 bond pair, and there is no lone pair in phosphorus. So you will get 5 as the answer. It will be sp3d. And for sp3d2, you can take s sub 6 as an example. And for sp3d3, we can have IF7 as an example. Okay. So one example. For sp3, we have seen two examples, right? H2O, NH3, and CH4 also you can take. And for sp2, we have taken BF3, and for sp, we can have BCl2. So yesterday we have seen that VSEPR theory, many examples we have studied there. So all those things you can take. HgCl2. So those are sp hybridized. Okay. So we can use this formula and get the hybridization of the central element easily just by looking at the thing. If carbon is bonded with one carbon with the double bond, means the hybridization of both the carbon will be sp2. If a carbon is forming only one bond, it is sp3. If it is having 2 bonds, then it is sp2. If it is forming 3 bonds, then it is sp. Okay, good. So any doubt from the hybridization part? Shall we move on to the next theory? So this is about the hybridization. If you're having any doubt, yeah, CN. CN is sp hybridized. I have already told you, no. CN is sp hybridized. It is forming triple bond with nitrogen, so it is sp hybridized. If a system is having 2 pi bond, then it is sp hybridized. Okay, here also you see this ethane is having 2 pi bond, no? 1 sigma and 2 pi. If 2 pi bonds are there, then it is sp hybridized. Only one bond pair. The other 2 bonds are formed by the lone pair of electrons. So it is only one, not exactly lone pair. It is resonance. Cn minus, no? It is actually Cn minus, not Cn. So it will be resonating between carbon and nitrogen. Fine, students. So now let us move on to the next theory, which is very important theory, like VSEPR. It is molecular orbital theory. Molecular orbital theory. So now coming to the postulates of molecular orbital theory, coming to the postulates, the postulate number 1 is the electrons in a molecule are present in the various molecular orbitals as the electrons of atoms are present in the various atomic orbital. You see here. So let me take this. This is hydrogen. Okay, this is hydrogen molecule, and here are the atomic orbitals of hydrogen. So I have 2 hydrogen, and the atomic number of hydrogen is 1. The electron will be there in 1s orbital, and like the electron is present in 1s of atomic orbital, it is also located in the molecular orbital also. So that is postulate number 1. Okay, electrons in a molecule. So this is the molecule, this is the molecular orbital, and these are the electrons. Electrons in a molecule are present in the various molecular orbital like it is present in the various atomic orbital. Got it? Now coming to the second postulate. Only atomic orbitals of comparable energy and proper symmetry combine to form molecular orbital. So here you see, 1s combines with another 1s. 1s can form the bond with 2s. Okay. 2s can form the bond with 2p because the energy level follows this order, right? 1s, 2s, 2p, 3s, 3p, 4s, 3d. So this is the order of energy level. So atomic orbitals, if they are of comparable energy level, the one which is nearest to it, they will combine with each other. Okay, 1s with 2s, 2s with 2p, or 1s with another 1s, 2s with another 2s. Like this, they are combining with each other. Okay, and the symmetry also should be proper. Okay, symmetry wise also it should be proper. If 2s orbital is like this, we should use the p orbital which is along this axis, because then only they can combine with each other. Let me take this as 2px. Okay, if you are taking 2s and if you are putting 2py like this next to it, if it is 2py, okay, it will not combine because the symmetry is not proper. Okay, so atomic orbitals of comparable energy and proper symmetry combine to form the molecular orbital. Okay, clear for all? Any doubt you have? Any doubt for anyone from the two postulates? Shall we move on to the third postulate? Yes, good. Now coming to the third one, an atomic orbital is monocentric while molecular orbitals are polycentric. So in atomic orbital, we have only one nucleus, so it is monocentric. And in case of molecular orbital, minimum we have two, and if three atoms are combining, we will have three. So in that case, it is polycentric. More than one nucleus is there, so it is influenced by both the nucleus, so it is polycentric in nature. Okay. Yes. Coming to the fourth postulate, total atomic orbitals combining is equal to the total molecular orbitals being formed. If two atomic orbitals are combining, two molecular orbitals will form. If four atomic orbitals are combining, four molecular orbitals will form. If six atomic orbitals are combining, six molecular orbitals will form. So that is the meaning for this. Okay. And here in this picture, you see two atomic orbitals are combining, two s orbitals are combining, and here we have got two molecular orbitals. One is sigma s and the other one is sigma star s. So these are the molecular orbitals. Okay. And here, these two molecular orbitals that is getting formed, they are called as bonding molecular orbital, and the other one is anti-bonding molecular orbital. So who is bonding and who is anti-bonding? The one which is present in lower energy to atomic orbital is bonding. So let me take energy is increasing in this manner, and this is the energy level of atomic orbital. Okay. Now let me take this as the energy level of this sigma s, and this is the this as the energy level of sigma star s. So here sigma s is lower in energy compared to atomic orbital. So those orbitals are called as bonding molecular orbital. So energy will be very low and the stability is more because energy and stability are inversely proportional. Okay. And the one which is present higher in energy to this atomic orbital are anti-bonding atomic anti-bonding molecular orbital. Since the energy is very high, stability is very low. Okay. Is this clear for all? When you combine these two, addition of the wave function leads to bonding, subtraction of the wave function leads to the anti-bonding orbital. Okay, we will discuss some examples in the upcoming slides. So this is the fourth postulate. Coming to the fifth postulate, the electronic configuration in various molecular orbitals are governed by the same used to follow to fill up the electrons in atomic orbital. So the three rules are Aufbau principle, Hund's rule, and Pauli's exclusion principle. We use these three rules to fill up the electrons in atomic orbitals, right? So we have to use the same three rules to fill up the electrons in bonding molecular, all the molecular orbitals also. So what is Aufbau's principle? What is Aufbau's principle? Electrons are arranged in the increasing order of energy level from 1s, 2s, 2p, 3s, it goes on. And what is Hund's rule? No pairing occurs until all orbitals of same energy level are half filled. Okay, you have to give equal distribution for the same orbital. Then only you have to do the pairing. So this is Hund's rule. And what is Pauli's exclusion principle? One orbital can take only two electrons, and those two electrons should have opposite spin. That is Pauli's exclusion principle. So we are using all these three rules while filling the electrons in molecular orbitals also. Okay. So is this clear for all? So these are the 5 postulates which are being used in the molecular orbital theory. All the 5 points are very, very important. You have to study all those 5. Okay. Now we will move on to some cases. So case number 1 is, I think using the molecules which have p orbital, I'll discuss one thing, one example with the molecule which has s orbital. Okay. So for hydrogen we have seen, right? Now let me go with the helium. Let me go with helium because helium is atomic number 2. So let me go with the helium. So for this helium, I want to draw the molecular orbital energy level diagram. How to draw that? How to draw that? Energy is increasing like this. First, I have to take 2 helium atom. What is atomic number of helium? 2. Electronic configuration is 1s2. So each helium will have 1s orbital. Each helium will have 1s orbital in which 2 electrons are located. So these are the atomic orbitals of helium. Okay. Now these 2 atomic orbitals will combine and they will give 2 molecular orbital. They will give 2 molecular orbitals. So these are the molecular orbital. The name of this molecular orbital is sigma 1s and the name of this is sigma star 1s. The star denotes the antibonding. That's all. Okay. Now I have to fill up the electrons. How to fill up the electron? 2 plus 2, 4 electrons I have. So go from the lower energy because we have to follow off bus rule, right? So we have to go from the lower energy orbital. So 1, 2, 3 and 4. Okay. So this is how we have to fill up the electrons and this is the representation of the molecular orbital energy level diagram for helium. Then if you go for lithium, what is atomic number for lithium? 3. So the configuration is 1s2, 2s1. So you can draw for 2s alone. Okay, you can draw for 2s or you can draw for both 1s and 2s also. So first go for 1s, then start with 2s. Then if you are going for beryllium, atomic number is 4. 1s2, 2s2. Then comes boron. So if I want to go for all the things are molecule, right? So B2. Atomic number for boron is 5. So for 2 boron, I will have 1s2, 2s2 and 2p1. So 2s2 and 2p1 are the valence orbital. Got it? So I will draw. Now from boron onwards, we have p orbitals, right? From boron onwards, we have p orbital. For p orbital, we have to follow something. So that thing only we are going to see in the next slide. Okay. So the atomic number of 1 boron is 5. And if I take 2 boron, it will be 10 electrons. And for carbon, 6 plus 6, 12 electron. And for nitrogen, 7 plus 7, 14 electron. So for the molecules whose electrons are less than or equal to 14, for these molecules, you have to follow this energy level diagram. Okay. So for 1s we don't have any thing. So it can follow the same way. And for 2s also no issues. When coming to this p orbital, we have 2p orbital for both the atom. It can be boron or carbon or nitrogen, whatever it may be, we have 2p orbital for all those, right? So for this, how many atomic orbitals are combining here? Here 3 2p and here 3 2p. So totally 6 atomic orbitals are combined. So they will form 6 molecular orbital. And the bonding is, so here and here one and above this one. So these 3 are the bonding molecular orbital. And these 3 are the anti-bonding orbital, which you can see. So what is the name of this bonding and anti-bonding? So this is called as pi 2px. So here in the slide, it is not represented properly. Sorry for it. So I'm writing here. I think you can understand from this. And here it is 2py. And the name of this bonding orbital is sigma 2pz. Okay. Now these 3 are the anti-bonding, right? So this is, just put a star, pi star 2px, and this is pi star 2py, and this is sigma star 2pz. So these 3 are the anti-bonding orbital. So how we are getting? We are getting a triangle kind of thing for anti-bonding as well as for bonding. Okay. So this is how you have to fill the electrons. And this is the energy level order for filling up of electrons. Okay. Below 2, above 1, and below 2, above 1 for both bonding and antibond. Okay. If you want to write the electronic configuration, start from the first. Go from this. First sigma 1s, then sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, which is equal in energy with pi 2py, then sigma 2pz, then pi star 2py, which is equal to pi star 2px, and the last one is sigma star 2pz. So this is how you have to write the electronic configuration. For atomic orbitals, we are writing no 1s2, 2s2. So like this you have to write. If you're having 2 electrons in sigma 1s, put 2. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Like this go. Okay. So I'll take one example. So let us do for nitrogen. We will do for nitrogen. How to do for nitrogen? What is the atomic number for nitrogen? 7. And for 2 nitrogen, we will have 14 electrons. What is the electronic configuration for nitrogen? What is the electronic configuration for nitrogen? It is 1s2, 2s2, and 2p3. Okay. So let me take this as the energy level diagram for nitrogen. So these are the nitrogen molecular orbital and these are the atomic orbitals of nitrogen. So in 1s I have 2 electrons. Okay. So 2 plus 2, 4 electrons are filled up like this. And talking about 2s, 2s also contains 2 electrons. So 2 plus 2 again, 4 electrons are filled up in this manner. Then coming to this 2p. So each 2p is having 3 electrons. 2p, 3. So 3 plus 3, 6 electrons. So 1, 2, 3, 4, 5 and 6. Okay. So this is how we have to fill. Now while writing the electronic configuration, how we have to do? Sigma 1s has 2 electrons. Sigma star 1s has 2 electron. Sigma 2s2. Sigma star 2s2. Then pi 2px is also having. Pi 2px is also having 2 electron. Pi 2py is also having 2 electron. Sigma 2pz is having 2 electrons. So you can stop up to this. You don't have to write all these things. Okay, you can stop up to that. So 2023 NEET question was asked from this only. So they gave 4 options. Okay, in NEET they have asked this year, last year. And they gave 4 options like this, and they have asked the students to find out the correct electronic configuration for nitrogen molecule. Okay, you just need to remember this pattern. That's it. Is this clear for all? Do any of you have any doubt? Shall we move on to the second case? If you're having any doubt, if any of you are having any doubt, just let me know in the chat box. Or if everything is clear, just give me a thumbs up or type yes in the chat box so that I can move on to the second case for the system which has more than 14 electrons. Or more than 14 electrons. Okay. Okay. Which part you want me to repeat? Ramnagar students, which part you want me to repeat? Or shall I go with the next case and explain you there? Which part? Anything specifically from the nitrogen part you want me to explain? No, if you want, if you're having doubt in any of the specific thing from the nitrogen or carbon, you can tell me, I'll explain. Or if everything, you want me to explain all the thing again, then we can see that in the next slide. Is that okay? From this slide, yeah, which part? Which part? Electronic configuration part or the molecular orbital energy level diagram part, or from which part? Energy level. Okay. So from the energy, electrons are arranged in the increasing order of energy level. Okay, electrons are arranged in the increasing order of energy level. From lower energy, sigma 1s, till the higher energy, it is slowly getting added. Okay. I don't know from what is your doubt exactly. Am I clearing what you are expecting? Or put me a question in the chat box. What is your question? Just let me know in the chat box. Type the question in your chat box. Okay, don't worry, okay? So I'll take the next case and explain you from the first again so that you can correlate that with this and understand. Okay, I'll explain with one more example. Fine. Okay. Take boron. So we have 3 examples on the slide, right? So you take boron. What is the atomic number of boron? What is the atomic number of boron? Can anyone tell me? We'll take boron as an example and try to understand this. Boron atomic number is 5. Very good. What is the electronic configuration? 1s2, 2s2 and 2p1. So start from this 1s. We have 2 boron. Each has 5 electrons. 1s2, 2s2, 2p1. And these two are the boron atomic orbital and this is the molecular orbital of boron. Okay. The center part we have the molecular orbital. In left and right we have atomic orbital. Now 1s has 2 electrons. Each boron has 1s orbital and each 1s has 2 electrons. So 2 plus 2 is 4. So here 1, 2 and 3, 4. Okay. And coming to the 2s, 2s also has how many electron? 2 boron is having 2 electron. So 1, 2, 1, 2. And here 1, 2, 3, 4. Okay. Now coming to 2p, each 2p is having 1 electron. So this is the first boron. This is the second boron. And 2p1 and here also 2p1. Now totally we have only 2 electrons in 2p. Now how to fill those 2 electrons? One goes to pi 2px and another goes to pi 2py. So this is how we have to fill up those 2 electrons because we have to follow Hund's rule. Hund's rule says that for no pairing occurs until all orbitals of the same energy level are half filled. Now here if you see the energy level of pi 2px and the energy level of pi 2py are same. So you have to give equal distribution, then only you have to pair up. Now we don't have electrons in case of boron to pair up. So we are putting 1 in each 2px and 2py and leaving it. Okay. Now if I have to give the electronic configuration for the system, I have to start from sigma 1s. So sigma 1s has 2 electron. Sigma star 1s also has 2 electron. Sigma 2s is also having 2 electron. Sigma star 2s is also having 2 electron, right? And pi 2px is having only 1 electron. Pi 2py is having only 1 electron. So with this you have to stop. Okay. If some others are also given, then they will give 0. Okay. They will put 0 here. If in the option, if these orbitals are given, they will put 0. Okay. Clear now? Did you guys get it now? Okay. Ramnagar, students, JNV Ramnagar. Okay, fine. So now let's go with the next case. For the system which has more than 14 electrons. So the examples are oxygen, fluorine and neon. So the atomic number for one oxygen is 8. For 2 oxygen, 16. So oxygen is having 16 electron. Fluorine is also having, fluorine is 9 plus 9, 18. And neon is 20. So all these 3 species have electrons more than greater than 14. Right. So in this case, which energy level diagram you have to use? There is nothing new. Okay. We're not going to use the entirely new energy level diagram. Just one small shift you have to do. Okay. What is that shift? Sigma star 1s, pi, sigma 2s, sigma star 2s. There is no change in all these. All these remain same. Okay. You don't have to change anything. You just need to change these two orbital. So in last case, we had pi 2px and pi 2py at the bottom, right? So bring that two orbitals has gone here and sigma 2pz orbital has come down. So here we have sigma 2pz and above that we have pi 2px and pi 2py. Okay, just do this shift alone. In the antibonding, no change. Antibonding has 2 below and 1 above, and whose names are pi 2px, and this is pi star 2py, pi star 2px and pi star 2py, sigma star 2pz. So there is no change here also. So here it is following an inverted triangle kind of shape, and here there is no change. So in the first case, we had orbitals like this. In the second case, we are having the orbital just because of the shifting of these two. Okay, clear? That's all. Now let me explain you this with one example. Just remember this shift alone, because in the exam, if they are asking you to find out the correct electronic configuration for oxygen, you should not do with like in case of nitrogen. In case of nitrogen, these two orbitals will go above, right? So after the sigma star 2s, these two will come. Then only this will come. Okay, but in case of oxygen, you have to interchange that. Okay, so while picking out the electronic configuration for the corresponding molecules, you will make this mistake. So to avoid this mistake, just remember this. Got it? Now we'll take oxygen. So starting with oxygen, the atomic number for oxygen is 8. Electronic configuration for oxygen is 1s2, 2s2 and 2p4. The two oxygen combines to form oxygen molecule, in which it also has 1s2, 2s2 and 2p4 electron. So 1s has 2 electron. Okay. So those two atomic orbital electrons are filled in the molecular orbital like this. And coming to 2s, it is also same. Okay, it is also same. And this is sigma 2p z orbital. And in 2p, how many electrons we have? 4 electron. So in 1 2p, 4 electrons are there. In another 2p also 4 electrons are there. Now totally how many electrons? 4 plus 4? 4 plus 4 is 8. Now I have to fill those 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. Is that clear? Is this okay? So now while writing the electronic configuration, put 2 here, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2p is it also 2, sorry, sigma 2p is it also 2, pi 2px is 2, and pi 2py also has 2 electron, pi star 2px has 1 electron, and pi star 2py has 1 electron, and sigma star 2pz has 0 electron. Okay, is this okay for all? Clear now? For fluorine also the same way you have to follow. Okay, for fluorine also do the same way. In 2p you will have 5 electrons for fluorine. So you'll have 5 plus 5, 10 electrons will be there. Now while filling 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this will be for fluorine. For fluorine, all the pi star will be fully filled. When you go for neon, for 1 neon, the atomic number is 10. And for 2 neon, atomic number, total number of electrons will be 20. So you will have 2p6 configuration, 2p6, 2p6. So 6 plus 6, 12 electron. So all the bonding and anti-bonding molecular orbitals will be fully filled in case of neon. Okay. So such an easy thing only. You just have to revise it to avoid all the confusions, and you have to just revise it. Then it will be okay. Shall we go with the applications of molecular orbital theory? So I have discussed the postulates, 5 postulates of molecular orbital theory, and the 2 cases to follow for molecular orbital energy level diagram. Very good. Now next we'll go with the applications. So what and all we can find out from the molecular orbital theory. So these 4 things you can find out from molecular orbital theory. Bond order, bond length of the molecule, stability of the molecule, and magnetic nature of the molecule. So all these 4 parameters can be found out from molecular orbital theory. So in BSAPR theory and valence bond theory, if you have noticed, we did not get any information regarding the stability, bond length, magnetic nature and all, right? Yes or no? So those theory didn't explain anything about the stability and all the 4 parameters. They just spoke about only the shape of the molecule. VSAPR theory gave the shape and geometry of the molecule, right? Valence bond theory also the same thing. It just gave the structure of the molecule. They doesn't talk about the stability. That is the main factor for chemistry, right? So only if we know if the given molecule is stable or not, we can study the chemistry of that particular molecule, because it is very important. So, but they didn't explain the stability or the other thing. But this molecular orbital theory will explain the stability of a molecule. From that stability information, we can study the chemistry of that molecule. So this is one of the very important theory you have to study. So let us see one by one. So moving on to the first application, I'll just discuss the first application alone today, and in the next session we can discuss the remaining thing. Okay. So in the next class we can complete this lesson and we can move on to the new lesson. So coming to the first application, which is bond order, all the 4 applications are very important. Just have a look in it. Bond order. So according to molecular orbital theory, there is one formula to find out the bond order. Already we have studied the definition for bond order, right? What is the definition for bond order? Do any of you remember the definition of bond order that we have discussed in the first class? While discussing the bond parameters, I have given you one definition, no, for bond order. Do any of you remember that definition? It is the number of bonds between the 2 atoms. Number of bonds between the 2 atoms is called as bond order. The same thing is followed here also, but in terms of molecular orbital energy level diagram and molecular orbital theory, we are finding out the bond order using one formula. It is Nb minus Na divided by 2. So what is Nb? Number of electrons in bonding molecular orbital, and this is number of electrons in antibonding molecular orbital divided by 2. Okay, divided by 2. Now, let me go to this oxygen case again. So in oxygen, how many electrons we had? We had the configuration like this: 2 electrons in pi star 2px and pi star 2py. Now take this formula. Bond order is equal to Nb minus Na divided by 2. Okay. So number of electrons in bonding molecular orbital. You can use this formula for all the orbital, or you can eliminate the s orbital and you can use it only for p orbital also. If you are using for only p orbital also, you will get the answer. Okay. So let me just eliminate all this. Okay, I'm not going to see the 1s and 2s part. I'm going to see only the 2p part. Okay. Now, how many bonding orbitals are present in the 2p? So these 3 are the bonding molecular orbital. So how many electrons I have in the bonding molecular orbitals of 2p? Can anyone tell me the total number of electrons present in the bonding molecular orbitals of 2p? It is 1, 2, 3, 4, 5, 6, right? 6 minus Na. Very good. How many number of electrons are present in antibonding? We have 3 antibonding, but we have only 2 electrons. Only 2 electrons are present. So it is 2 divided by 2. So 6 minus 2 is 4. 4 by 2 is 2. So the bond order for the oxygen molecule is 2. So that's why we have double bond between the 2 oxygen atom. Okay, number of bonds between the 2 oxygen is 2. Okay, how it is 2? Why we are putting 2 bonds between 2 oxygen? Because the bond order is coming out to be 2. Okay, so like this, you can get the bond order using the molecular orbital energy level diagram, or you can use this trick table to calculate the bond order. So how to use? You have to just calculate the number of electrons. Using this number of electrons, you can straight away find out the bond order. Okay. So start from 10, number of electron. If it is equal to 10, then the bond order is 1. Okay, 11. So take from 10 till 18, take this 14 as a reference. Okay, that is a standard point. So if the number of electron in a molecule is equal to 14, then the bond order will be 3. Bond order will be 3. Now for 13, 12 and all, you have to reduce 0.5, 0.5. And in the bottom part also, what you have to do? Reduce 0.5, 0.5. Okay, so for boron, we will have 10 electron, and for neon, we will have 18 electron. So just do like this and get the bond order. So in oxygen, how many electrons we have? 16 electrons, right? So 8 plus 8, 16 electron. Then the bond order is 2. You don't have to fill the electrons in MO diagram and get the bond order. Straight away, you can get it like this. Okay. So I'll explain this in detail tomorrow with you again, and then I will move on to the next application. Is that okay? Because it is already time for you guys. So I'll just stop here. We will continue this in the next session. Don't worry. So if you're having any doubt, you can ask me. You can ask me in the next class, okay? I'll ask me in the next class, go through this. Thank you. Thank you so much, students, for listening the lecture. Take care. Bye-bye. Yeah. Thank you. Thank you.